So let's talk about overall conversion. So I've given you a little equation up there for overall conversion of A, this one. So the discussion that we're going to have today and Wednesday is going to be couched in terms of a single reaction. Because the math is a little bit easier for a single reaction, all of these concepts still hold for multiple reactions. There's nothing wrong with that. It's just the calculations get a little bit more tricky. We can always define a conversion of a single component for multiple reactions. It's just that we've seen that the math, when we're trying to dump those into something like ODE 45, sorry for the pause in the podcast, that was a software update. I didn't do it. So we're going to talk about overall conversion a little bit, because that is a useful quantity when we start talking about multiple reactions. The reason that it's useful is pretend that you are your own boss, right? Your boss comes to you and is a complete moron, has no idea what's happening inside his or her own plant. All the boss can see is we are bringing in raw materials over here and we are putting out product over there. What's the conversion that we're talking about? If you have multiple reactors inside your system, as a clever engineer that you all are, you're going to want to say, well, the conversion in the first one is about 20%, and then we get about 19 and 20% in the remaining ones, and then you talk about the recycle, how that makes it a little bit better. And at that point, your boss is completely zoned out. In fact, your boss doesn't care for you anymore. It causes a whole HR problem because he calls you a nerdy reactor engineer, and you're like, that's not fair, and then you go to HR. And then they fire you, and it ends up that you were producing a really important drug, which is no longer produced, and massive numbers of people die. Because overall conversion was ignored. It's really important.
Are you speaking from experience here?
Because of the settlement agreement, I can't tell you whether or not I'm speaking from experience. So what do we mean when we say overall conversion? It's exactly that. What if you took the plant level view of your entire system? So overall conversion, let's imagine you had multiple reactors, and there's all kinds of things going on, right? So the output of one goes into the other. Maybe it splits off partway through. These streams go into something like a CSTR. They come out, this stream rejoins over here, goes through another reactor, comes out over here, and maybe some of it recycles back. Right? And assume all of those are reactors. You can define a conversion for each one of those reactors, right? If I take any one of these individual reactors, I can define a conversion of A for that particular reactor, because I know how much was, presumably I know how much was fed into that reactor, and I know how much is coming out, so I can calculate a conversion. The conversion that we're talking about is if you take a bigger view, which is to say our entire process, imagine a control volume around the whole thing, eventually has basically a single input and a single output for practical purposes, right? You might have some side streams like flares or purge streams or something like that, but there's probably only one stream from which you're collecting product. This is how we define the overall conversion, XA. The superscript I'm putting there is OV for overall. And so we calculate that based on the two quantities of A. We have a molar flow rate of A coming in. And sooner or later, after we go through all of our reactions, we have FA coming out. Right, and then so XA overall is just defined as FA in minus FA out divided by FA in. So it's useful in the sense that, yeah, it gives me a sort of overview of the entire system. How well did I do given a certain amount of product or a certain amount of reactants that I started with. But its real usefulness comes in when we talk about the two topics we're going to spend most of today and Wednesday on, which is if I do have multiple reactors in certain styles, it's actually easier to do calculations based on overall conversion than it is on individual conversion. Notice, let's give some arbitrary numbers to these reactors. So let's say this is reactor 1, this is reactor 2, this is reactor 3. And so there's a conversion associated with each one of these that I'll put up here in the superscript as X superscript number of reactor, right? So there's a conversion associated with reactor 3, another one with reactor 2, etc. It is not the case that the conversion in 1 plus the conversion in 2 plus the conversion in all of the other ones, whichever last one that you had. We don't really have a superscript that means this is the last reactor, so I'll just say N for N reactors. That is not going to be equal to the overall reaction. Right? It's a simple way to prove this to yourself is imagine you have 2 reactors in series and the conversion in each is 50%. Well, if you start off with 100 moles of stuff and you convert 50% of it, then you've got 50. Then if you convert 50% of that, you're going to end up with 25. The overall conversion there is not the sum of the conversions of the individual reactors. That would be 100%, but we've only converted 75%. That would also suggest that if I had reactors that are like 70, 70, and 70%, that you could get more than 100% conversion. So the conversions of individual reactors do not sum to the overall conversion. They are directly related to each other. You can use a couple of equations on here based on the definition of conversion and figure out what that relationship is, but it's not necessarily an easy representation to have. So the point here is we're not actually going to look at these conversions very much for the next 2 lectures. The primary conversion that we're going to look at is this one, the overall conversion. The individual conversions are the ones that we've been dealing with up until now because we've always dealt with a single reactor. You briefly saw 2 reactors on the current homework, which should be hopefully a little bit more clear as we go through this discussion as well. So let's also look at some material balances. We're going to assume for most of the, actually, do we need to make that assumption? No. Okay, we don't. We're just going to look at the material balances. It would all work if you had the energy balance. It just makes your life a little bit more difficult. So let's not worry about it at the moment. If we have a CSTR, we saw that the design equation for this, the material balance, was that the volume of the reactor was equal to the flow rate times the conversion of A, the inlet flow rate of A times the conversion of A over minus RA. We're going to look at the material balance for all 3 reactors and rearrange them in a way that isolates a particular group just because we have found by experience that this is a useful group to look at. So let's rearrange this. We'll leave V on one side, and then we'll pull out X sub A. The remaining term that sits inside here is this term that we're going to get familiar with, which is FA naught over minus RA. What does this mean? If I have V is equal to FA naught over minus RA times XA, there is a clever little plot that I can make to graphically represent what the volume is of my reactor. This is the plot that was on the previous slide. If I plot X sub A versus FA naught over minus RA. The question of how do I figure out what FA naught over minus RA is it kind of depends on what system you're dealing with. It could just be given to you. You could have tabulated data for rates as a function of conversions, or you could have to calculate it based on some assumption about hitting equilibrium or something. There's nothing inside any of those terms that we're not already pretty familiar with, right? The rate is dependent on conversion. We know how to express that in terms of components if we need to. It's not particularly often that we will for this kind of example, but imagine there is some curve associated with FA naught over minus RA as a function of XA. That's not an uncommon curve that we would establish. What this equation says is if somebody gives me a conversion, let's say you want a particular conversion of whatever that number is, I can determine the volume of my reactor by only knowing what FA naught over minus RA is at that particular point. So if I find out where this point intersects, what this equation says, the material balance, is that if I calculate this area on the plot, this is the volume of the CSTR that I need. And that's it. There's nothing else that if we were somehow given that plot, wherever that data came from, of FA naught over minus RA as a function of XA, and somebody said, tell me how big the reactor needs to be in order to get that particular conversion, this particular conversion down here. I could go onto this plot and figure out what the area is of that box, and that would tell me what the volume is of the reactor. The usefulness of that is kind of limited, because that's not exactly a difficult calculation to do, until you compare it to the other types of reactors that we have. For the packed bed reactor, or the plug flow reactor, it doesn't matter which one you want to deal with. We saw that the conversion as a function of volume, V, was equal to RA over minus FA naught. We know if we're dealing with a packed bed, we can replace that volume and the RA with weight and an RA prime, because we can go back and forth. Those two are directly related. So since everything else is dealing with actual volume, we're just going to leave it as volume, but we can go back and forth if we need to. If we rearrange this one to get a similar result, the volume of our reactor isn't equal to the product, it's now equal to the integral from 0 to whatever x we want of that same quantity, FA naught over minus RA times XA. Or, sorry, not XA, dXA. So that calculation is a little bit trickier, but it has a nice graphical interpretation in terms of that plot that we already created. So if you sketch another one next to it, here's our XA, plot exactly the same thing, which is FA naught over minus RA. And imagine you've got that very same curve. Remember that curve that you've got here, this black curve, it doesn't care what kind of reactor you have. It's the same for all reactors. It's only a function of the rate of reaction down here in FA naught. What's the graphical interpretation of it? Not area of the square, area under the curve. Right? So these two are similar, except now if I want that same conversion, and I want to know what the volume is, I no longer calculate the area of that square, I calculate the area under the curve. And the area under the curve represents the volume of a plug flow reactor. Also the volume of a packed bed reactor. But since those two are directly proportional, I'm just going to talk about plug flow reactors so that I don't have to keep writing PFR or PBR. It's the same thing. Right, and this is the, oh, sorry, yeah, go ahead.
So my question is, if minus RA is a constant value, will you will yield the same graph in the same shaded region for both the CSTR and the PFR?
Correct, yes. Which means it doesn't matter which reactor you choose, you're going to get the same conversion for the same volume.
Is that true for reactions where minus RA is not constant?
No, if minus RA is not constant, then you've got a situation like what we've got here. Yeah.
When you're getting the volume of a packed bed reactor for that one, is that the volume including catalyst or without the catalyst? Because the catalyst like picks up an amount of space.
It's the volume occupied by the catalyst when you dump it in there. So the proportionality factor is the bed density. That'll tell you, okay, for the volume that I calculate here, multiply that by the bed density, that gives you the mass of catalyst needed in your reactor. So these particular plots have a name associated with them because back in the day, if you were clever, you could get stuff named after you, which doesn't seem to happen as much. I'm still waiting for the Drew's method for something. These are called Levenspiel plots. The way to create a Levenspiel plot. Actually, maybe not the way to create it. There's only one step to create it. Important features of the Levenspiel plot. Step one is how do you create it? It's a pretty easy plot to create. You're going to plot FA naught divided by minus RA versus the conversion of A. That's it. There's not a lot that goes into creating this plot. There are no other assumptions that get baked in there. How you come up with FA naught over minus RA can depend on what information you have available, but let's assume for the moment you have it because it's going to be given to you in most cases. You can use the Levenspiel plot in one of two ways to quickly do a calculation where if you don't have the math available, if you don't have, for example, MATLAB sitting in front of you, and everybody knows there's a particular instance where it's important to know how to do this calculation and you don't have MATLAB in front of you. What instance is that?
An exam.
An exam. So two ways that you might see this used. If you're given XA, you can get either the volume of a CSTR. The volume of a CSTR is the box area. So box area just means that blue shaded region that I showed a minute ago. Or you can get the volume of a PFR as area under curve. These two instances are generally the easy ones. Mostly because they don't require any kind of iteration. You can go wherever you need to on the x-axis, draw a line up, find out where it intersects that curve, and then either figure out the amount of area underneath the curve if you need a PFR, or the amount of area given by that box. There's not a lot in there that's tricky. The trickier one, just from a standpoint of I need to do a couple of calculations a few more times, is to go the other way around, which is if you are given the volume of a reactor, we can guess our value of X until we end up with the volume from our guess is equal to the volume that's given. So it's using the plot the other way around. Now what I'm telling you, the information that you are being given here is what if the area under that curve needed to be a specific value, or the area of that box needed to be a specific value. It can involve a little bit of trial and error to figure out the exact value of X that I need in order to figure that out. But you don't need anything other than the plot. This one is a little bit harder. Again, not harder, right? You're still calculating areas under curves. It's not like it needs MATLAB or anything like that. It's just a little bit more tedious because you don't know exactly where to go on that x-axis. These are sort of the basic aspects of a Levenspiel plot. The real utility of the Levenspiel plot comes when you make an additional assumption about your system. And so this is going to be the third point that we have. This one, oh, I lost my other pen. Hold on, I need my stars back. All right, I guess I'm not going to get my nice gold stars, so I'll put a blue star here. This is the reason why we use Levenspiel plots. If you have reactors in series, So that's the first step that's very important, is that they have to be in series, and they have to have no side streams. What is a side stream? A side stream could be a recycle stream. It could be a purge stream that came off partway through. It could be fresh feed that was added to the subsequent reactors. Basically, if you have a series of reactors where the output of one reactor is fed directly as the input to the next reactor, then we can use the Levenspiel plot, which I'll abbreviate as LP, Levenspiel plot, for all the reactors. If you do something like this, the critical feature is that X sub A on the x-axis gets replaced by XA overall. So that's an important distinction to keep in mind, because the utility of this makes it so easy to calculate things for multiple reactors that you can sometimes convince yourself that it can't be this simple, and you sort of tie yourself in a knot trying to figure out, well, I know XA overall, but does that mean I know what the individual conversions are? You can probably figure out the individual conversions, but the Levenspiel plot may not make that particularly easy for you. The real utility is what I had discussed before, which is now you can take a sort of a plant level view of what are all of your reactors doing. How many of those reactors do I need? What size should they be? And in what order do I need them? Also, what style of reactor do I need? Usually the reason that you can get away with that is because volume is typically directly proportional to cost. If you need a bigger reactor, it usually costs more to get a bigger reactor. Consequently, we're looking to get the smallest possible reactor that still gives us the highest possible overall conversion. That'll generally end up to be the most profitable process. So let's look at a couple examples of how this is executed when I actually have a system. Let's say example 1 is, what if I have a CSTR followed by another CSTR? What does that look like on a Levenspiel plot? First, the system that we're describing is one CSTR with its output going directly into another CSTR. So I'll make this one blue. We'll call this reactor 1, and the second reactor red, and call that reactor 2. So again, keep in mind that what we are calculating here is the overall conversion. So X sub A overall. If we were to put this on a Levenspiel plot, I'm going to draw a lot of these, so I'm going to get myself a straight line here. That's not a straight line. That's an awful straight line. This is what makes engineering hard. That's pretty good. If we have a plot like this, that probably took longer than if I just drew it, so I'll probably just draw it next time. FA naught over XA. Keep in mind that this XA now becomes XA overall. And I'm going to keep using roughly that same shape for FA naught over minus RA. We'll look at what happens in about 10 minutes if that shape is not the same. What this equation is, or sorry, what the Levenspiel plot is saying is that if I want to know what the volumes and conversions, or sorry, overall conversions are for these reactors, I need two squares. So the first one is going to go up to here, and the area under this square this is going to be the volume of reactor 1. The part where it can get a little bit, I'm going to move that over here because I need to label some stuff. The part where it can get a little bit tricky in terms of how do I interpret this is what's the conversion for that reactor? We're not really defining what the conversion is for that particular reactor. We're talking about what's the overall conversion of component A at that point inside of our system of reactors, our series of reactors. It is a coincidence that after the first reactor, it happens to be the same conversion as that reactor, but everywhere after that, it's not. The value that's coming out here is the overall conversion that you have achieved after reactor 1. It is, I guess, not coincidence. Only for that very first reactor does that coincide to the actual conversion inside that reactor. The reason being, the next one, we are going to plot right on top of this on the same Levenspiel plot, which would be over here. The volume of the second reactor is represented by this rectangle on a Levenspiel plot. So this is the volume of the second reactor. What did that volume achieve? We are not mentioning here what the difference is between the reaction conversion in the first one and the conversion in the second one. All we're tracking is how did we do on increasing our overall conversion. The overall conversion just got added right on top of the first one. So now we have the overall conversion due to the second reactor is whatever that value happens to be over on the right-hand side. This is the utility of the Levenspiel plot, which is that if I'm interested in the overall conversion, I can stack these areas right on top of each other, and the further along the x-axis I go, the more overall conversion that I'm getting. But as I mentioned, I think previously, don't try to do the following, which is XA, actually that would be red, wouldn't it? XA overall due to reactor 2 is not equal to the conversion of A in reactor 2. Nor is XA overall to, actually, nah, let's just leave it like that one. No, that's a good one to have. The difference here. There are times where you can get this to work out, but usually it's not the case. I'm going to have to double check that math. XA in reactor 2. So the difference between those two. If you look at, let's say this one went from 50 and then up to 80, that doesn't necessarily mean that the conversion inside reactor 2 was 30%. Because we saw before that usually these things don't add up. There may be special cases where that is the case, but usually they don't. The easiest way to interpret these plots is to, for a moment, forget about what the individual conversion is for each one of those reactors and only look at this from the standpoint of overall conversion, because that's the tool that we're using on the x-axis down here. So if you ignore for a moment what the individual conversions are in the reactors, this becomes a particularly useful method for calculating things. The things that we will calculate will be shown to you in a moment. Let's look at the other kind of version. So if you have a CSTR followed by a CSTR, you get something like this. If you have a PFR followed by a PFR, and you look at the same thing as FA naught over minus RA. I'm going to try to make that plot look the same. Your first reactor for a given volume will be able to achieve a particular conversion. Your second reactor just gets tacked right on top of it. And so is there any utility to using two PFRs in series instead of one giant PFR? Not particularly. The volume is going to end up being the same. It doesn't matter if I use two PFRs in series or one really long PFR, which sort of makes sense if you interpret a PFR as a tube. It doesn't really matter if I take two short tubes and put them together or if I just started off with one really long tube. It's about the same thing no matter which way I look at that. And now you can get into all the various combinations. Imagine you had a CSTR followed by a PFR. And you took this same plot, XA overall, FA naught over minus RA. Your first one is a CSTR, so you'll get some level of overall conversion denoted by the box, the area of this box. And then your PFR comes afterwards. Let's move that a little bit here. So this one represents the volume of your PFR, and this one represents the volume of your CSTR. So you can begin to answer questions of which, based on that curve of FA naught over minus RA, how many reactors do I need, and which ones are the ones that I should use, based on the general assumption that smaller reactors are less expensive. If I can design a reactor that doesn't need to be as big, I can probably buy it for a little bit more, or a little bit less money. So would you recommend using a CSTR followed by a PFR if that's your FA naught over minus RA curve? Probably not, because if I replace that first CSTR with a PFR, I can do a little bit better, right? If I were to look at this area underneath, if I could replace that as with a PFR, I could get this same overall conversion here, but with less volume. How about the other way around? What if I did a PFR followed by a CSTR? Kind of a similar idea, right? I probably still shouldn't do it because the volume of my CSTR, if I replace the second one with a CSTR, is going to be proportional to this square that I've got, right? Which is going to add this space in here as additional volume that I don't really need. If I could have a PFR instead of a CSTR, I could do that with a slightly lower volume. So if you have a curve like this, which is sort of monotonically increasing, it really only makes sense to use a PFR. If you use a CSTR, depending on what your needs are for that reaction, you're probably paying a little bit more than you need to because there's some volume in there that could be reduced if you were to switch to a plug flow reactor or a packed bed reactor. How do I calculate? I'm going to simplify one of these. Let's look at a different, I was going to put it right on top of here, but there's enough stuff in there already. Let's look at this CSTR followed by a PFR and try to calculate the volumes of each reactor. Again, this is for CSTR followed by PFR. The volume of my CSTR is equal to FA naught over minus RA. But this FA naught over minus RA is evaluated where?
At the first reactor, the beginning of the first reactor?
Yeah, at the overall conversion at the outlet of the first reactor. So this is evaluated at XA overall at reactor 1, and then we have to obviously multiply this by XA overall reactor 1. If I want the volume of the PFR, I still need an integral. It's going to be FA naught over minus RA times dXA. Well, that's not really times dXA, just dXA. What are the limits of my integral?
0 and x.
What is it?
0 and x.
0 and x.
XA overall.
XA1 to XA2 overall. So if I want this particular integral, if I want that volume, I need to go from XA overall reactor 1 to XA overall out of reactor 2. Where that math comes from is a little bit less than obvious. You can prove to yourself that that does have to be the case. This is another case where if you don't overthink the Levenspiel plot, that equation becomes pretty obvious. If I need to know the area under that curve, well, the value of the curve is right here. Let me erase some of this just so it looks a little bit better. This part of the curve here is my FA naught over RA, and I need to know the area under that curve from this particular point to this particular point. Right, so those represent the limits on my x-axis. So again, when you're dealing with the Levenspiel plot, the easiest way is to sort of compartmentalize the concept of a Levenspiel plot and say, the only thing that I'm interested in a Levenspiel plot is the overall conversion of A, not the individual conversions in different reactors. Then you can come up with these sorts of equations a little bit more easily because you're just calculating areas on plots. And so these bounds on an integral become something like what you would have seen in whatever your equivalent of calculus is, the first one where you're learning that the integrals represent areas under curves. How about one more before we look at the various curves in 5 minutes? If I had a PFR followed by a CSTR, the curve that I'm going to get on a Levenspiel plot, the first reactor is my PFR, which is here. The volume I need for my CSTR is this square. So this first point that I have is XA overall achieved coming out of reactor 1. The second point that I have is XA overall achieved after exiting reactor 2. The volume of my PFR is the same integral in the sense that it has the same integrand, FA naught over minus RA times dXA. Now what are the limits? 0 to XA overall 1. Which is the standard volume of a PFR that we've seen previously. How about the volume of a CSTR? We're going to need a couple of terms. We need at least FA naught over minus RA. Where do we evaluate this one?
XA overall 2.
XA overall 2. And then what do we need here? 2 minus 1. Right, so this one looks like XA overall 2 minus XA overall 1. Again, you can, if you want to sit down and do the material balances and talk about the conversions of individual reactors, you can show that this relationship is true, or you can look at the plot and say, how do I calculate the area of that red square? Well, I need to know the height of the square. The height of the square is given by this term. And I need to know the width of the square. The width of the term is given by this term. Or the width of the square is given by that term. Yes, that's what I said. And so if you've got a Levenspiel plot with multiple reactors on there, the easiest way to derive what the volumes are of each one, if you need to actually calculate them, is to just use a little bit of intuition about what those plots are and calculate that area. You can always verify that with the material balances, but the math gets a little bit, I would say, irritatingly complex just because there's so many variables that you have to carry around. So tell me which reactor you would use, or plural, which reactors you would use, and in what order. If you had a Levenspiel plot that looked like that, and you wanted to get the highest conversion you could. You can use any number of reactors. One what?
PFR.
One PFR. What if you had a Levenspiel plot that looked like this?
Means it's a reverse
Not necessarily, well, maybe. There is probably a reversible element, but what kind of reactors, plural or singular, would I use? Why CSTR? Yeah, you'll get smaller volume, right? If I come out here to this X, the volume of the reactor is here. Right? Which is much smaller than if I needed the area under the entire curve. So this one would be 1 CSTR. How about this one? And I wanted a big reactor, or a big conversion out here. CSTR, then PFR. Because my CSTR volume will be here, which is smaller than a PFR. And then as I move past that and I want to get up here, now my volume is a PFR, which is smaller than the corresponding CSTR. So this one looks like, oh, sorry, CSTR. Followed by a PFR. Which is pretty ridiculously simple compared to actually calculating the individual conversions of those reactors, but it does require that special piece of information, which is the actual FA naught over minus RA curve, which is not always something that we can come by. And then I was going to do the last one, but somebody already mentioned the last one. What about this? Doesn't matter, right? Area of a square is the same as the area under that curve. So this one, it wouldn't matter. And it can go on and on, no matter how complicated that plot looks, even if it looked something like that, you could go through element by element and say, what's the smallest possible volume that I need for each one of those? Okay, so that's the utility of a Levenspiel plot. You're going to practice that with a lot of different ones on the first homework of 7, which doesn't actually get posted till Wednesday when the next homework's due. That's all I got. If you've got those exams, please give them back to me so that I can post them outside my office, and I will see you on Wednesday.